As long as I sit in this hot spring, the water and I are in thermal contact with one another. If this pool were not continually replenished with hot water, then the water and I would reach eventually the same temperature, which is called thermal equilibrium. Well, this pool is constantly refilled with hot spring water. Now that water comes from deep underground where the earth heats it, and it is piped into the pool right here, and it is very hot. In effect, it's about 105 degrees as it comes out of this tube. Well, as we sit in thermal contact, this water is continually replenished, keeping it hot. Now, because this water is always hot, the water is transferring thermal energy to me. As long as that difference in temperature exists, then we will continually experience that thermal energy transfer. Well, the 0th law of thermodynamics explains how two objects in thermal contact can achieve thermal equilibrium. The 0th law of thermodynamics sets the stage for understanding temperature. And if we're able to understand temperature, then we are able to define and apply all the rules of thermodynamics. We've gone ahead and done a great demonstration here with different oranges and an environment. Let's translate that to our understanding in our note format here on the board. So let's just review quickly. We initially had an environment in which we placed an orange that we called C and we're using to represent our thermometer in an environment of isolation with another orange that we'll call A. Now, what we do is we allow them to reach thermal equilibrium. This is a little bit of shorthand that I use so I don't have to keep writing those big old long words. Thermal equilibrium. TEQ, thermal equilibrium. We also put orange C in with orange B and again let them reach thermal equilibrium. Well, our conclusion was this. If C was allowed to reach equilibrium with A and then allowed to reach equilibrium with B, and we recorded that temperature, we recorded the temperature at equilibrium with A of C, and we recorded the temperature of C when at equilibrium with B. If these two temperatures were the same, then we said that objects A and B were at the same temperature and therefore in thermal equilibrium when in thermal contact with each other. So if we were to put A and B in this environment, there would be no energy exchange because they're at the same temperature. So our concluding statement here is that if our thermometer, that's how I meant to say, if object C has a temperature reading, temp reading, that is the same when in equilibrium with A and B, then we say that objects A and B are at the same temperature. Then with A and B, then A and B are at the same temperature. And thermal equilibrium. They're at the same state in thermal equilibrium if our thermometer C has the same reading. Well, this little demonstration right here goes to illustrate what is known as the 0th law of thermodynamics. 0th law of thermodynamics. And the 0th law of thermodynamics says this. It says that if an object A and B are each individually in equilibrium with a third object, C, then A and B are in thermal equilibrium with each other when placed in thermal contact. Okay? And so that is our definition of the 0th law of thermodynamics. Again, it says that if objects A and B are individually in equilibrium with object C, then objects A and B are in thermal equilibrium with each other when in thermal contact. This seems like an incredibly large duh statement, okay? And it seems so simple. It seems so logical. It seems so basic. You know, of course that's the case. Well, this, although it's so simple and basic, the 0th law of thermodynamics becomes the basis of our ability to describe what temperature actually is and what the properties of temperature are. And so to consider temperature is to consider the device called a thermometer. So let's now start talking about what a thermometer actually is.